Hi, everyone. My name is Pranav. I'm an engineer at a company called Provable. We are a labs code that is really into ZK tech. So today, I'm pretty excited to talk about ZK-powered payment channels, but only sort of. See, what happened was when I sat down to write this talk, I realized that there were so many core conceptual pieces to go over that instead, we're going to take the long way and talk a little bit more generally about private payments using ZK, and finally touching on these interesting ideas like payment channels, stablecoins, compliance at the very end. So as a little bit of an overview, we're going to take some time to set the stage. Then we'll actually dive into private payments, how the model looks like abstractly. Then we're going to expand on that a little bit, talk about the hybrid ZK VM that we've designed at Provable and then actually instantiated in Aleo. And then finally talk about the cool use cases at the very end. So with that, let's just jump into it. So first, I wanted to just set into a frame of mind what the anatomy of a payment looks like. Now, for most of us, whenever we make a transfer, a payment using crypto, we're looking at some UX that looks like this. Now, under the hood, this is implemented very differently across different chains. But abstractly, we'll reason about a model that looks like this. Here, we have off-chain a user Alice, and on-chain a ledger, which for a token program contains some state. Here, Alice has 8 credits, 8 tokens, and Bob has 2. And what Alice is going to want to do is send Bob 3 credits over via the network. Now, the way this looks like in Ethereum, in Bitcoin, kind of abstractly here, is that Alice will first generate a transaction. That transaction will specify the person she wants to send to, the amount, and a signature. And Alice is going to fire that over to the network. The network is basically going to take a look at this transaction, process it, verify that it's well-formed, verify that the signature is correct, and then update the state. And at a high level, this is like how payments work like, transfers work like in the account model. But if you squint your eyes a little bit, you'll also see that this is how they work in the UTXO model. There is a public ledger. It contains some public balances, and that tracks how much everybody has. There's a fundamental problem here, though, and the issue is that all transactions are public. This means that the actual UX that we expect in payments, in transfers, in money, isn't actually represented in these sorts of constructions. When we send money, we expect that only the 2 parties who are interacting actually get to see the details of the payment. And this is just a fundamental problem that kind of blocks a lot of crypto use cases. If you're a whale, you're very cautious about moving your money around to prevent people from tracking your expenditures, so on. If you're any user, right, you're basically under the assumption that you can be tracked. So in this talk, we're going to work out how we can use a different model to effectively support private payments and get the kind of UX that we want. Now, before we get there, we're going to have to talk about ZKPs, but I'm going to keep this super, super high level and oversimplified. There isn't a huge need for technical ZKP materials, but there's a bunch of really good resources online for this stuff. So for the purposes of this talk, when I refer to zero-knowledge proofs, I'm going to refer to ZK snarks specifically. And what that means are zero-knowledge, succinct, non-interactive arguments of knowledge. Now, if we were to dive into ZK, there's a lot to unpack here. But for today, all we're going to care about is the zero-knowledge component. Basically, that the private inputs to the proofs are not revealed to anyone who has the proof itself. Another way to think about this is that with the zero-knowledge proof, I can create a proof pi that proves that I know some value x, which is private, such that some result y is equal to f of x. And in this case, y and f are public. Now that we've kind of run through this overview and kind of set the stage for payments and ZKPs, let's take a look at what a private payment actually looks like from first principles. Basically, we have in this model a different kind of instantiation of state. Before, you had this ledger which tracked for every account, every user's balance. Instead, in this model, we're going to track these objects called records. And records are individual data blobs. You can think of them as encrypted envelopes, each with a public ID, which is enforced to be unique, and some encrypted data, which is encrypted to the owner in the record. You know, if you're coming from like the Bitcoin space or familiar with like the UTXO model, this effectively looks like encrypted UTXOs. So in this setting here, Alice has a record that she owns that is on chain, but the balance and the fact that she owns it is encrypted. So only she knows her balance here. And same with Bob. Bob has a balance. He knows that he has 5 tokens, but no one else knows this information. Now, if Alice wants to send, let's say, 2 tokens to Bob, she's going to form a transaction. And now there's a lot of parts here, and we'll go through them one by one. The component in the red is the records that Alice is going to use as inputs. So she's going to reference records that exist already on chain and say that she's going to be spending these things and then producing the blue records that you see out there. So in each of the blue records, you'll see that there are 2 new records created, one called 3 and one called 4, and one basically debiting Alice the amount that she has remaining, and one giving the amount to Bob. Additionally, there are also 2 proofs attached to the transaction. And these proofs basically will assert, using zero-knowledge proofs, that the transaction is well-formed, so that the encrypted data was created correctly, and that Alice actually owns record ID 1, and that the balance is conserved. So Alice didn't mint money out of thin air. And with this, she'll fire it over to the network, and the network will verify these zero-knowledge proofs, as well as check that the transaction's well-formed. For example, that the record 1 actually exists on-chain, and then update the ledger. And the way the network updates the ledger is basically the network will invalidate the record that Alice wanted to spend, and then append the 2 new records that Alice has created. Now, you can follow along this model to basically work through it and see how Bob might, condense his state. So if Bob, right now has 2 records, 2 and 4, each with 5 and 2 credits respectively, Bob can basically fire off a new transaction that takes 2 and 4 as input and produces a new record 5, which asserts that, just basically combines the 2 records and fires it off to the network and subsequently gets updated. So at the end of it, Alice has transferred 2 credits over to Bob, and Bob has aggregated his private balance. And in this whole process, nobody else knows the actual balances of Bob and Alice, or even knows off of looking at a transaction that it was actually Bob and Alice that sent money to each other. Now, we kind of spent all this time talking about how we can move away from this account-based ledger model, similar to like stuff that we see in Ethereum, the EVM, so on. But there are actually some good things about it. When transfers are public, it means that they are easily auditable. It's also very easy to manage this state and actually implement these kind of designs, versus these record-based UTXO models have UX issues, as well as, you just got to do a lot more heavy lifting to implement something like this. But there are desirable properties in both. So in Aleo, ZKL1 that we've contributed to, help build up, we've just kind of combined the 2. We have in the VM in the network a public ledger that tracks public balances, as well as a private ledger that tracks your private balances. Now, what this means is if we have this kind of like traditional world where, you have public on-ramps, a centralized exchange, a bridge, and just public transactions where Alice and Bob can send money back and forth, move them on and off, and so on, you now get this private dual world where Alice and Bob can also move into the private domain and transact between them. What's kind of unexplored here, which is kind of pretty exciting, is what are the private on and off ramps look like? How do you construct private dexes? How do you construct private bridges? And this is a bit of an open question, but a very exciting space to kind of look at. Now, I kind of fudged things when I said Aleo just combines the public construction, the account model, and the private construction, the encrypted UTXO model. We actually have also instantiated a custom designed VM where developers can upload their own programs and more generally write code that works with private logic as well as public logic. And instead of just looking at payments as one, as the core problem, this virtual machine here kind of treats payments as a use case, as a specific program on the network. And with that, you can start to explore more production-grade stuff. So, kind of the sort of pseudo-topic of this talk, payment channels. So payment channels are kind of an interesting idea. Basically, one approach to scaling the speed of crypto payments. Alternate approaches are like actually building a full-purpose L2. This is another approach that kind of got some popularity in the early days in the Bitcoin community. The way it works is basically at a high level, you have two parties who want to transact, send money back and forth to each other, Alice and Bob. And what they're going to do is they'll go through a couple steps where they will open up a payment channel via an open and an acknowledgement, and then send as many transfers back and forth with each other, and then finally close the whole thing. The way this works in the traditional sense is that opening and closing is on-chain, and in Bitcoin and any kind of like EVM style or account-based construction, this part is public. But because we've designed this thing with records and private state, privacy actually almost comes for free. You can just copy the existing constructions out there, and you have private state channels where settlement is actually truly private. And then because we designed this virtual machine where you can kind of arbitrarily define other functions, other logic, you can use that to add in more rich spend conditions to your payment channels. So it's not only just balances going back and forth, you can add extra conditions that do something more interesting. Maybe require some identity verification, maybe require some minimum balance, something like that. Another dimension to actually, implementing these things in production or actually creating a product out of them is compliance. So we spent all this time creating a private way to transfer money, but there's a problem in doing that, and that's you're basically fundamentally doing something illegal. With private money, it means that people can kind of launder money quite easily if you don't have guardrails in place. So with this, we're also thinking a lot about, with privacy, how do we design compliance? And what's really interesting is that zero-knowledge proofs, while giving privacy, also give a very natural mechanism for adding in compliance that's also private. Now, at a very base level, if you're looking at compliance for private transfers, the basic thing that you need to do is make sure that a party interacting doesn't come from a set of blacklisted addresses. And this kind of fundamental idea is known as, or this thing bakes down to something known as set exclusion. And we know how to do this with Merkle proofs. It's fairly straightforward. And it's also fairly straightforward to instantiate these in zero-knowledge proofs themselves. But other than set exclusion, you can do a lot more interesting things. Basically, again, we're just going to use zero-knowledge proofs to kind of prove arbitrary properties about the users who are initiating or receiving payments. So some interesting things you can do is use a zero-knowledge proof to provide some identity verification. You can use a ZKP to check that your transactions are under some limits, or that another set of assets have a certain amount of exposure before firing off a transaction. You can require credit checks. You can require checks on user history all through ZKPs. You can enforce sanctions. You can add requirements that users come from specific locations. And you could even do provenance for funds before they're actually sent through. Here, things do get more creative. There do need to be parties that provide, this sort of like raw data in the case of identity. But it's really kind of an open space for application developers to really add in whatever compliance measures that they want. So it's kind of like based on each use case, anyone can really design whatever piece that they need here. So at Provable, we've basically been exploring ZK tech, building this stuff out, and its main instantiation is in Aleo. Aleo is a ZKL1 that kind of implements this zero-knowledge virtual machine with all these principles baked in. So developers can immediately go on it, use a language called Leo to develop their dApps, and immediately have this ability to write hybrid applications that interact with public and private state. And yeah, that's all I have today. This is the general high-level idea, and if anyone has any questions, I'd love to dive into it a little bit more. I think we'll get a mic over there.
Yeah, I mean, can you make a quick comparison of the Aleo, like the Provable Aleo, like the payments you just talked about, with like things like Zcash or something like that?
Yeah, it's a really great question, right? So just to repeat the question, how do we compare payments on Aleo to something like Zcash? And the interesting observation is that the baseline ideas of Zcash, where you have these kind of like public and then shielded domain, is instantiated as, instead of a core protocol level implementation as it is in Zcash, in Aleo, this is a programmable piece. So to actually do this in Aleo, you write a program that you upload to the VM, and you get these kind of privacy elements in there. So whereas in Zcash, it needed to be a native asset, here developers can build their own programs, add their own compliance mechanisms for specifically their own use cases, and upload it on chain and run them. Great, thanks for listening, everybody.